Distinguished colleagues and guests, good afternoon. It's November 12th, 2021, the year 2021, 2 p.m. Moscow time. And we're beginning the panel session for the defense of the thesis by Gleb Shuvalov. The thesis is submitted for the academic degree of the candidate of sciences in physics and mathematics. The specialization is 118, mechanics of hard body under deformation. The topic of the thesis is the effect of surface stresses on topological defects formation in layered structures. Under the order issued by the Academic Secretary of St. Petersburg State University as of August 19, 2021, number 8138/1, I, Yulia Peronina, Doctor of Sciences in Physics and Mathematics, Associate Professor, Professor of the Department of Computational Methods of Deformable Body Mechanics of St. Petersburg State University, was appointed the chairperson of this dissertation board. The order also approved the members of the board, namely Svetlana Bauer, Doctor of Sciences in Physics and Mathematics, Professor of the Department of Theoretical and Applied Mechanics of St. Petersburg State University. Alexander Volkov, Doctor of Sciences in Physics and Mathematics, Professor of Elasticity Theory, Department of St. Petersburg State University. Ulyanovskaya, Doctor of Sciences in Physics and Mathematics, Associate Professor, Leading Researcher of the Applied Research Lab of the Institute for Problems of Mechanical Engineering of the Russian Academy of Sciences. And remotely, we have another member of the board, Holm Altenbach, Doctor of Technical Sciences, Professor of Otto von Guericke University from Germany. Do you hear us? Holm, do you hear us? Yes, I hear you, but I need to turn off my microphone. Yes, otherwise we'll have noise interference. Svetlana, hello. Okay. And we also have our candidate for the degree, Gleb Shuvalov. Hello. And we also have the thesis supervisor, candidate of Sciences in Physics and Mathematics, Associate Professor of the Department of Computational Methods of Deformable Body Mechanics of St. Petersburg State University, Sergei Kostyrka. And I would like to inform you that the panel session of the dissertation board is being recorded and broadcast on the St. Petersburg State University website, and it is also interpreted from Russian into English and vice versa. And currently we have an email address posted on the page with live broadcast of the board session, and all the listeners can submit their questions to Mr. Shuvalov online. The questions regarding the thesis or scientific discussion. And thus people can participate in the scientific discussion. These questions will be forwarded to me by our technical service, and I will read them out during the discussion. The questions must be related to the presentation, the speech of the applicant, and the content of the thesis. And do not forget to give your name and position if you submit a question. Questions that have nothing to do to the scientific discussion, with the scientific discussion, or the dissertation text, or anonymous questions will not be voiced. Under the order on the procedure of granting academic degrees at St. Petersburg State University, approved by local normative acts, the session of the dissertation board is valid, providing 2/3 of the appointed board members are present. And the total number is not to be fewer than 4 people. Our dissertation board consists of 5 people. Everyone is with us today, including one member of the board who is working remotely. And we have multimedia connection with this member of the board, so we have a quorum, and I ask the representative of the Department of Dissertation Board Support to fill out the attendance list. So our agenda is as follows. Our session should not last more than 2 hours. First comes the chairman's presentation about the documents submitted by the candidate for the degree and their conformity with the requirements. Then chairman's replies to questions, if any. Then we're going to listen to the brief presentation of the candidate, providing an overview and findings of the research, 20 minutes for that, followed by questions to the candidate regarding the presentation, and then the candidate will answer the questions. Then the reports on the thesis. The board members will be taking the floor in turns to provide their reviews and questions. And proposals, if any, 10 minutes per speaker. 6. The chairman's report on the thesis and the candidate's comments about the reports on the thesis and replies to the questions. Then we're going to have open discussion, if anyone is willing to voice their ideas, positions, or ask specific questions. So we'll have time for that. 10 minutes per speaker. And at that, I kindly ask you to fill in the registration form if you want to submit a question, and don't forget to introduce yourself before I give you the floor. Then the chairman will ask questions submitted during the broadcast via our website. I would like to draw your attention to the fact that written questions that will take more than 10 minutes to read them will not be voiced. Then the candidate's replies to the questions. Then the presentation of the candidate's thesis supervisor. Then we can have a 5-minute discussion before the open balloting on conferring or non-conferring the academic degree. The discussion of the results of the defense is not broadcast, so that's possible if we want to do that. Then we're going to have open balloting. We'll count the votes and record the results into the protocol. Then we're going to make a decision on whether to confer the academic degree or not. And finally, we're going to listen to the candidate's closing speech, 2 minutes for that. So, distinguished colleagues and the applicant for the degree, are there any questions or objections? No objections? No questions. Okay. No objections? Okay, so let me start. And first of all, I would like to kindly ask you to switch off the sound on your mobile phones. Thank you. So we start. The chairman's presentation. The thesis by Gleb Shuvalov for the academic degree of the candidate of sciences in physics and mathematics. The specialization is 118, mechanics of hard body under deformation, is titled The Effect of Surface Stresses on Topological Defects Formation in Layered Structures. The thesis was approved for the defense by the order of the Academic Secretary of St. Petersburg State University as of August 5th, 2021, number 7814/1. Mr. Shuvalov has prepared his thesis at St. Petersburg State University. He was our PhD student, and Sergei Kostyrko, candidate of Sciences in Physics and Mathematics, Associate Professor of the Department of Computational Methods of Deformable Body Mechanics of St. Petersburg State University, is the thesis supervisor. 5 published works describe the research findings. They include 2 papers published in peer-reviewed journals recommended by the Ministry of Education and Science, and 3 papers in publications indexed in Web of Science and Scopus. And actually, Gleb has 3 more publications not given here in the list on the topic of the thesis, and they are also indexed in Web of Science and in Scopus. And all the documents provided by the applicant for the degree comply with the requirements, and they are found in the certification file of the applicant. And curator of the defense, member of the dissertation of the Department of Dissertation Board Support, has all the copies of these documents. And before I give the floor to Mr. Shuvalov, I would like to ask the members of the board, distinguished members of the board, are there any general questions to the applicant? Is there need to consider the whole list of documents submitted? I believe there's no need for that because everything was checked already. Okay, no questions. Therefore, Gleb, you have 20 minutes. Late structures are widely used in electronics, optics, and healthcare. However, during the production of such structures, we may have certain defects, and that is a barrier when we want to improve the functional characteristics of devices. And one of the key processes that lead to the formation of defects in such structures is associated with morphological instability. Initially, this roughness of surfaces may lead to the formation of indents due to diffusion processes. And it should be mentioned that there are some positive points in relief formation for hard bodies, for example, roughness that emerge on the surfaces and borders of materials, that is the basis in a range of applied goals. And we know that diffusion may happen in volume and on the surface of material. However, in strained structures, the main contribution to relief is given by surface diffusion. The first theoretical study of morphological instability of solid bodies under diffusion was conducted by Mullins. He described the development of grooves on the surface of crystal. Then Azar and Tiller detected that the surface of hard body under one-axis stress is unstable if we have a wavelength that exceeds the critical value. The same result was obtained by Greenfield and Saranovitz, and it was experimentally supported by Torrey, Balabar, and other studies and other researchers. Here is the comparison of experimental results with theoretical ones, and we see that critical value expression coordinates well with the data of experiment. And currently we have a lot of studies conducted that expand the morphological instability model of Azar-Tiller Greenfield to analyze voids, microchannels, and inclusions. And in these studies, they considered the structures with linear sizes from several hundred of nanometers to several microns. Therefore, the impact of superficial elasticity was ignored because it was seen as negligible. But it should be mentioned that in the recent years there's a growth of interest to the formation of nanostructural relief, and we know that in nanoscale bodies we see the growth of elasticity role. Therefore, we decided to expand the morphological stability model, considering the surface elasticity, and in order to take it into account, we devised there were a range of models, but Gerten and Murdoch was the most suitable model. They offered to use an elastic membrane that is associated with a hard body, but this membrane has different characteristics. And based on this model, a lot of studies are conducted. This model shows scalability effect characteristic for nanostructures, and here you see the dependence of concentrations in the close proximity of the curved margin. And we see that with the increase of wavelength, the impact of surface elasticity is growing. And in our study, we'll also use the Gerten-Murdoch model. And the main goal of the study is to develop and analyze mathematical models of morphological instability of free and interface surfaces of hard bodies and film coatings. The main goals are here on the slide. We should develop evolution equations that describe the kinetics of development of relief of free and interface surfaces, and other goals that were given on the slide. The thesis has 4 chapters that have the following models. First of all, a morphological instability model for the surface of multi-layer film coating at superficial diffusion, considering the surface tensions. Then morphological instability models for nanostructures of solid body, of ultra-thin film, and also the border of materials taken into account the instability. First chapter is dedicated to morphological stability of the surface of the multi-layer film coating. So we want to consider the smoothing procedure, and the model of coating deposited on the substrate is heterogeneous semi-plane that is given by the unification of B1, B2. Interface borders are linear, and perturbations are described by sign function. And talking about weak perturbations, we believe that the wavelength is much higher than the amplitude. The material for each layer is isotropic because a geometric model is infinite semi-plane, and here we have longitudinal stress that is permanent, and other indicators equal 0. And we believe that there is a sigma s pressure, and in mechanic equilibrium on the free margin, we use the Laplacian law, and at interface borders we have no leaps of transition vectors and tension vectors. And at every point of time, the system is mechanic equilibrium, but not necessarily it is in thermodynamic equilibrium. And in order to relax the stress and minimize free energy, the body can change the form of margins. And within the framework of this model, it is provided that transformation of atoms of the surface happen due to superficial diffusion, and the flow of atoms is proportional to the gradient of chemical potential. The chemical potential is described by this function. Here we have all these characteristics described on the slide, and also the speed of movement in normal direction is described by equation as well. And here we have the speed of change of the form of surface. Within the framework of this model, it is believed that superficial energy does not change during deformation, and specific energy of deformation is found when we resolve the plane problem. In order to resolve this problem, we use the Brekov approach, which is based on the methods given on the slide. Integration of evolutionary equation leads to the following dependency of amplitudes of perturbations on the parameters of the goal. The critical value of the wavelength of curvature is defined based on the 1.12 condition. If initial roughness of the surface has a wavelength less than critical, the diffusion will lead to the smoothing of the surface. As an example, we consider two-layer metallic film system. Lemma parameters correspond to aluminum characteristics and materials. Poisson coefficient coincides, which is suitable for metallic structures. And in this case, we study the impact of down layers measuring rigidity. And here you see the dependency of the speed of change on the wave length, considering different rigidity characteristics and the thickness of layers. So the critical value is the intersection of axes with horizontal axis. And the backline is here on the slide as well. And we use Azar-Taylor formula here. Here we see the dependency of the speed of change of amplitude at 100 nanometers. And we also studied the influence of the sign of longitudinal efforts. And we studied the difference between expansion and compression. Here you see the results on the table. Based on the analysis of the results, we made the following conclusions. The critical values of the wavelength grow with a drop of relative rigidities. The impact of relative rigidities on morphological stability of free surface of multi-layer film coating increase with a drop of thickness, and other conclusions given on the slide. And in the developed model, we provided that superficial energy does not depend on the deformation of the surface, but for nanoscale structures, its impact has an important role. And in order to take this elasticity into account, we used Gert and Murdoch model. It was used for the first time. Therefore, we devised morphological instability models for ultrasound films and connection margins. The second chapter is dedicated to the study of morphological stability of the surface of solid body with nanoscale relief of surface at a single axis compression or expansion. The model is a semi-plane beam, and the borders are described using periodic function. You see this condition 2.2. Longitudinal efforts are permanent here. And according to Gert and Murdoch approach, the main material and superficial layer are considered like two phases of one material, and the main material is considered as elastic semi-plane, and covered by a membrane. So we should have 2.3 conditions. And in order to describe the elastic behavior of the superficial layer, we use simplified equation of superficial elasticity. And here you see all the provisions. An equilibrium state of the surface is described by Laplace-Young law. And material is isotropic. It is provided that in order to minimize free energy, the form of surface will change due to superficial diffusion, and the equation that describes the change of amplitude look like that. And as in the first model, and here we will take into account the change of surface energy associated with deformity of the surface. And in a simplified Gerten-Murdoch model, superficial energy can be described in equilibrium 2.8. In order to integrate this equation, we need to define superficial energy, and here we used the approach provided by Grekov, and the solution is found in the first approximation of perturbations method. As for the integration of this equation, it shows the following dependency of amplitude to parameters of the problem, and here you see how we define it. Right. As an example, we considered aluminum, volumetric superficial parameters. Are given here on the slide. They correspond to aluminum, and surface level parameters were obtained in a number of works, and they depend on crystallography orientation and other factors. Therefore, they were varied in the work. And in order, and we also study the superficial rigidity and study the residual pressure and stress. And on this slide, you see the dependency of speed of change of amplitude on the wavelength of perturbations. And the left graph shows the range of wavelengths of morphological stability. And to the right, you see the distribution of chemical potential in equilibrium and non-equilibrium states. And we also study the impact of surface parameters, the scale of longitudinal stress. And we made the following conclusions given here on the slide. And the main conclusion is that the critical values of the wavelength grow with the growth of superficial rigidity and residual surface pressure, and with the drop of longitudinal stress. This model can be used for the analysis of morphological stability of film coatings in cases when the thickness of the layer is higher than the curvature wavelength. And in this case, the impact of substrate can be neglected, and the thickness will be taken into account in the next model. So the third chapter is dedicated to the analysis of morphological stability of ultra-thin film coating. As a model, we've chosen HF thickness, and it is a heterogeneous semi-plane, and you see its characteristics here. 3.2 are the conditions of eternity, and here we see the materials of substrate and material that are isotropic. And here we see the summarized law of Laplace-Young, and continuity conditions are described. The change of amplitude looks like 3.6 formula, and also in order to integrate this equation, we need to define the density of elastic energy and surface energy. So we need to resolve the elasticity problem here. And finally, we have this dependence of amplitude of perturbation on time and physical and geometry parameters. And as an example, we considered metallic system. The film parameters correspond to aluminium characteristics, and we have relative rigidity, longitudinal rigidity of free surface, residual surface stress, and longitudinal stress, and the thickness. And here you see the dependency of speed of the dependency of change of speed of amplitude, and we studied the interface characteristics change. We studied relative rigidity characteristics, superficial stress, and longitudinal stress characteristics. And based on the results, we formulated the following conclusions. And the major one here is that in case of rigid or soft substrate, the critical values of the wavelength grow or decrease with a rise of thickness of the layer. And diffusion can be observed not just on surface of the solid body, but also at the margins of connections. And as a model of the compound solid state with one axis stress, we consider two-phase plane, and we have the periodic function, and for eternity we have the following conditions: 4.2, and according to Gert and Murdoch, interface border of B to B1 phase are considered as different phases, and at that volumetric materials are considered as elastic semiplanes, and interface layers as an elastic membrane connected to them. Mechanical equilibrium is described by a summarized Laplace-Young law. Here you see delta sigma leap of pressure at interface border. Coherence conditions are described by 4.5 expression, and is provided that self-organization of tense border happened due to superficial diffusion, but the flow of atoms in every phase is proportional to the gradient of chemical potential. And we obtained this expression that describes the change of amplitude of perturbations in time, and in order to integrate it, we needed to define the superficial and specific deformation energy in the right part of the equation, and therefore we find the solution to the elasticity curve problem, and we see these conditions that allows us to find the curvature wavelength that will provide morphological stability of the boundary. As an example, we considered a structure that had a lower layer that corresponded to aluminum, and elastic parameters are given here on the slide. And on the slide you see the dependency of speed of amplitude change on the wavelength of perturbation in different elastic parameters of the system. We studied the impact of longitudinal and interface rigidity, residual pressure, and the conclusions are formulated. The major conclusion is that the critical value of wavelength grows with the increase of interface longitudinal rigidity, interface residual pressure, and relative rigidity, and also with a drop of longitudinal stress and diffuse coefficient. Thus, in this work, based on the correlations of thermodynamics and elasticity theory, we devised theoretical models that describe the change of the form of free and interface surfaces of hard bodies, and we define the conditions at which we are going to have morphological stability, and we studied physical and geometric parameters' impact on the growth of relief of free and interface surfaces. That's it, and I'm happy to take the questions if there are any. Thank you. I have a question to the members of the board, if there are any questions to our applicant on the report. No, we're going to listen to the reviews later on. Can you please tell me on slide 15 this second summand is not taken into account in your formula, or do you take it into account? Just a second. I'll flick to the 15th slide. 1.8. No, the second summand is not taken into account in the first model. It was provided that there's no dependence, and why do you give it here? But okay, it doesn't matter. I have one question regarding Gert and Murdoch. You said that they use this model for membranes, but essentially there's a membrane or a thin object that can withstand both extension and compression. Yes, indeed, it can be either compressed or extended. So that's a thin layer, and the thickness is not taken into account, yes. I'm not sure what Gerton and Murdoch said. Maybe they used membranes, but that was not clear for me. Thank you. So if there are no other questions, let's shift to the speeches of the members of the board with their estimates and questions to the applicant. And I would like to remind you that the applicant can answer all the questions at once or after each review, and I offer to answer the questions after each review. So do you agree with that? Yeah, I believe it's best. Okay, no objections about it. And as all the reviews were already published on the St. Petersburg State University website, so that everyone could get acquainted with them, I offer to give just the key points and the questions. Any objections about it? None. Okay. So, first of all, I would like to give the floor to Holm Altenbach. So, Professor, please, you have the floor. I won't give you what I've written in my review. Overall, I was very satisfied with the work because within this year I saw a lot of works, and I would say that St. Petersburg is one of top places. If we talk about the narrative and quality of work, everything was clear, and even a non-expert may understand something in this thesis. And overall, across the text, I had just one comment, and I fixed this question in my review, and I would like to read it out because I believe it is really important. So these thin layers on major body, the question is that there is this minimal thickness and maximum thickness when your theory works. Because I believe that, as always, there are certain limits of applicability, and sometimes it's easy to understand them and sometimes it's not. And what's your case? Thank you so much for the question. In this work, certainly, the thickness of superficial layer is much less than thickness of coating, but basically it's hard to give the general assessment. If we talk about the sources that we studied in works on molecular modeling, they considered the curve of the plane, or in Miller and Shannon works, the thickness of planes were considered as 5 nanometers, and interface surface layer was considered as several atom layers. And if we talk about other assessments like Altenbach, Yeremiev, Morozov work, there was an assessment that the thickness of the coating, if we take the thickness of the coating into account and if we can compare it with Gerten-Murdoch model, then the solution will coincide up until with rather high accuracy. But still, these theories give relative results. And as for the lowest limit, we can use this approach while we are able to use continuum mechanics in order to describe the discrete structure. Professor, are you satisfied with the answer? Yes, I know this answer because Ramajan and others, they gave it. The continuum mechanics allows us to get very delicate scale, even the size of atom. The question is, how can you formulate it potentially? And the second part of your answer is also correct, because you can't give the margins for sure, because if we knew that, maybe we could be even smarter, but finally no one managed to do that, so I fully agree with the answer. Thank you. Thank you. Alexander Volkov. Well, basically, I like this work. It should be mentioned that it is not the first work of a kind, and our department has been developing such approaches for a long time in order to describe superficial layers and stresses and strains. And Gragov's works should be mentioned first and foremost here. So it's not surprising that this work was tested on this department, and it was also tested on the workshops of the department. Therefore, the credibility is supported by that as well. That's, I believe, the best test that anyone could imagine. But as all the my review was published and it's positive, I would like to dwell upon the critical remarks that I had. Unlike Professor Altenbach, I can say that it's hard to understand this work for a non-expert because there are a lot of unexplained formulas and notions. Therefore, to my mind, it's rather hard to read it. And if I was not familiar with models of Krakow and similar models, it would be hard for me to sort it out. And as for specific remarks, I won't mention the misprints that I found in the work. But this formula 1.9 that you have in the thesis, it does not sufficiently describe the essence of this last summand, the dependency of change of energy on the curve, on the curvature. Because curvature here is the most important notion, because it changes during the growth of this island. And I would like to get more details about that. And you just give the summands and say that they describe the impact of curvature change during the movement across the surface on the normal. That's it. Then the second remark associated with the use of this term free energy. Well, the chemical potential, strictly speaking, that's the Gibbs energy. That's free Gibbs energy computed per one atom. Therefore, the author should, I believe, describe it in details, how you computed the Gibbs potential, maybe entropy could be somehow assessed, because you write about internal energy and then call it free energy. So I did not like this style, you know. And the last remark out of these important ones is that you do not give any numerical values. So what are the examples of critical values of wavelengths for relief for different stress cases? I'm not sure how long do you need to wait for relief when you have half a micron to form, whether it will be quick or no. So as a technologist, I wanted to know that whether you can assess it maybe in hours or minutes. So I've already mentioned I won't give you the misprints. So that's, I believe, it. Thank you so much for the questions and for the remarks. I agree with all the remarks. And as for the questions, I'll start with a question about full energy within the framework of this model, because we expanded as a Tiller-Greenfield model. As full energy, we saw the energy of the surface and volumetric energy. Therefore, we assess the change of energy or superficial and volumetric separately. And there was a question about the last summand in the expression to measure energy. Here on the slide, I gave the change of surface energy with the change of the border, and the boundaries are changing at speed Vn, that's normal velocity. And based on the derivative parameter, we have the following expression, and I've given it here in the frame. And the first part is reduced with a part that corresponds to the changes in volumetric phase, because periodic system and isolated system, we believe that for such systems, we believe that energy does not come from anywhere and it does not go anywhere. Therefore, these values will be equal, but they will have different signs. So part of volumetric energy will shift to superficial energy. And the last summand here is an integral from OS divided by Vn ds. I believe if you included it into the thesis, it would be nice. Okay, thank you. I forgot the... Yes, the second question was about numerical values and about free energy. How do you shift from internal to free energy? And about numerical values. Okay, as for numerical values, here we did not consider the relief change dynamics because we had no such goal initially. But if we talk about experimental data, essentially the scale is rather high, from 2 or 3 hours to 10 hours for the formation of relief. And in the graphs, you see the velocity at vertical axis. So it seems that you can use the speed to define how long do you have to wait for the transfer of effects for a certain distance. I believe you use some diffusion coefficient here. Non-specific diffusion coefficient, because here you have this given velocity, and if we talk about diffusion coefficients, essentially the scope of values is 10 taken to the degree of -18 and so on, and the order of amplitude is as follows, as you see on the slide. So we scaled them up like that, and essentially we define the dislocation of boundary in the normal direction. Therefore, in directions along the surface for these long distances, we did not carry out this analysis for that, but further on we'll try to take that into account. Okay, and as for free energy, yes, as full energy we've taken the surface energy and volumetric energy. Okay, but free energy, so open up any book and it will always be extracted this entropy from free energy. Did you assess it somehow? Did you compute it somehow? We did not assess it. The temperature is stable. And entropy? We did not estimate it, but I believe we can say that it seems to be permanent as well. Okay. Yes, we just took this point from the initial model. Okay. So, Alexander, are you satisfied? Yes, sufficiently, more or less. And as for other answers, I believe it will be placed on the website. Other remarks that were not that critical. In the review. Yes, okay, so there's no need for that, to read them out. So other remarks should not be mentioned, I believe, because they're dealing with the style and such things. Okay, thank you. Well, I can say that I agree with Alexander Evgenievich that you could have better wording and better structure. And, you know, I had to read a lot of other things to understand the work, but I had two discussions with Gleb, and he explained me some things that pose certain difficulties. And the comments are just the same. I have just one point associated with misprints and narration, and also I would like to mention that credibility of the results received in this unit. You say that quality theoretical results coincide with the best known theoretical experimental results, and you said that you discussed it on conferences, but essentially what kind of experimental data are you talking about? So what's the coincidence here? It's not fully described in the work. And I did not mention it, but once again, credibility say that the results are published, but that's not sufficient condition, because we know when people there are cases when it's not the case. But just for the future, to bear that in mind, that that's a form of wording. And maybe for me it's just more I'm used to using non-dimensional values. In this case, it's easier to assess the applicability limits of the results. But in such an approach, we already discussed it with Gleb, and I understand that maybe you should have left dimensionless values, because all the work that you are referring to, they use this nanoscales as well. But in such an approach, I believe you should have discussed the applicability limits of results, and this is seen in the first chapter, particularly when it's finished with specific 2 or 3 examples, and after that you make certain generalized conclusions. So I believe you could add up more details in the thesis, because in the report I believe you already corrected something that we mentioned in the text. And what's nice about this work is that you outlined the plans for the future. It's always nice to read about such plans, so I believe that this work should get a positive mark. Thank you so much for the review and for the comments. I'll try to take everything into account. And as for, should I answer? Yes. As for applicability of borders, the lower border, the lower limit can be described using continuum models, and as for the upper limit, well, that's not the upper limit of applicability, but as for about the upper limit of necessity to take it into account, because when the size grows, our model gives the same results as Azar-Taylor-Greenfield model. But if relief wavelengths are in the range less than 100 nanometers, in this case, this int is insignificant, and I try to demonstrate it here on the graph. With the dependency of concentrations of stress, because a stress state gives the highest contribution to the model. And as for experimental data, yes, indeed, I tried to describe them on the slides of the presentation as well. And all the models can be reduced to a Azar-Taylor model for solid body without coating. So essentially, well, this model is supported by experimental and theoretical data. So that's my answer. Okay. Yes, I'm satisfied. Okay. And Yelena, please. Yes, I also agree with colleagues, because as for the style, I did not like the style, because every chapter includes a lot of repetitions from what was already mentioned in the previous chapters. So it would be nice to not to have all these repetitions, especially when you provide Google law in every chapter, so you know it's a bit strange. Also, I have insignificant remarks about definitions, formulas, terms used, membrane that Helm already used, and interface boundary that is sometimes used as the division between the phases, and in this case chemical potential is just the thermodynamic power that shifts material from one phase to another, and you have just a compound body, and the chemical potential has a different value just for diffusion. I believe you could have divided it a bit. Next point. more specific one about the wording of boundary conditions for boundary problems. It was unclear how you form these conditions on the margins. Do you apply stress, or are these free borders? Because you said that you consider the impact of compression and expansion at the set force on the border. So I believe you should have described it more, not just saying about some the boundary values. And there's a question why you introduce this condition for the rotation of polar particle, because you consider non-polar mediums, and from your problem setting, this condition was not quite clear why we need it. And also regarding the 4th chapter, yes, it was unclear how you introduced the metric coefficient in evolution equation of the boundary, because you got kinetic equation for normal component of speed and you give it for the growth of boundaries across the vertical axis. It's clear that kinetic coefficient recalculates this normal component, but you had to guess that. So it needs to be described. And the 4th chapter, I had more questions here. First of all, as I can agree with you when you talk about superficial diffusion with free borders. Here the superficial layer is different and the diffusion goes along the surface, and it's different from the volumetric diffusion, but in any case you have a diffusion inside of the material, therefore it's not clear how can you ignore the diffusion in the volume and how can you consider just superficial diffusion. Maybe you use certain characteristics of the surface, but it would be nice to describe it in detail. And also there was a question on the form of boundary. It is taken as the baseline because you always write that you study morphological stability, and morphological stability provides for an addition of small perturbation to initial baseline form. So I believe you should have described it, what is the initial formula, or whether it was equilibrium, whether it had equilibrium, and whether it's a source of internal perturbations or not. So these explanations were not enough. Then I fully agree with Svetlana, who said that I would also prefer to have it in non-dimensional scale. You give all the results in nanometers, but as you said, the boundary conditions for eternity, if you considered the borders and the sizes in meters, comparing to eternity in meters, nanometers, they are too small. Indeed, therefore it's unclear where your theory can be used in what dimensions and margins. I believe you should have described it in more details. And as Svetlana said, if you would have non-dimensional values, it would be easier to show the range of applicability, that you can use the theory when the relation of your layer to other layers is less than something. And just a wish to share, for this practical use of the results, it would be more useful to formulate the conclusions in not in a qualitative but in a quantitative manner, because you give them as ideas. The thicker the layer, the higher the impact. So certainly it would be nice to get some more exact recommendations here. And finally, the last thing, from my point of view, it would be useful to give some quantitative comparison of the obtained results with experimental data or with numerical data obtained by other authors. But overall, I believe that the work deserves the academic degree, the award of the academic degree of the Candidate of Sciences in Physics and Mathematics. Thank you so much for the review and for the comments. I agree with the comments, and I would like to specify some points. can I answer the last question at once? In my presentation, I tried to give this comparison. Yes, I saw that there were a lot of things corrected in the presentation, and we discussed it. As for border conditions, indeed, why I consider single axis stress and the conditions are set for eternity, because they're not defined on the boundaries, because in any vertical cut the distribution of stress will differ, and as there's no margin here, we use this approach here. This approach was used in other works as well, for example Grekov, though indeed we could consider side stress and we got marginal effect, but in this case we don't have it. We don't have this marginal effect. Well, I forgot the questions once again, so I'll look at your reviews. Yes, I agree with all the comments. And as for metric coefficient, you answered this question, yes, yourself. Yes, but you had to guess. Yes, it would be nice to have it described. As for non-dimensional type, yes, I agree with that. In some cases there were these difficulties due to dimensional effect, but still some effects could be given as non-dimensional ones. And as for the applicability borders, here my answer will correspond to the answer of Svetlana Mikhailovna. And as for the question about interface border, in a range of works where they don't consider phase transition, they use this term interface boundary in English works. That's interface, and we have interface boundary and connection boundary. I decided to leave this terminology here, but maybe for people who are working with other fields, maybe there can be some kind of interference. I will specify it in the future. And as for the question about the angle of rotation, indeed, here in linear elasticity theory, we don't bear that in mind, but considering the used approach in the problem when we define the potential, we take into account the rotation angle, and the fixation of rotation angle allows us to consider the stress and deformity regardless of the movement. Maybe this condition was a bit of an excess, but still we decided to include it in the work. I believe I missed some of the questions. Yes, the form of boundary. Well, essentially we were based on the problem setting. In initial boundary was flat boundary with certain temporary perturbations, and therefore I have some misunderstanding about what you mean by initial boundary. If we talk about initial boundary that has that we considered whose morphological stability we considered, then that's plain morphological stability. And yes, certainly it should be stable. Flat form is stable, yes. Yes, that's why I have this question. So we considered boundary with weak perturbations. Yes, and this initial perturbation, what kind of perturbation? It was periodic one? No. So you have this one and perturbation on this boundary, or where? Well, initial boundary is already with perturbation. So we already have perturbations here that are described by small parameters, and in problem setting we already included it. Okay, thank you. Elena, are you satisfied with the answers? Yes? Thank you. Well, finally, I'm going to read my review. The work, I believe, demonstrates high qualification of the applicant in numerical and analytical calculations, but I agree with the previous speakers as well that unfortunately it has certain drawbacks, but they are just in the narration, because it's clear that it was just some omissions and they do not give us incorrect results, so they are not critical. And also, as Yelena, I had a comment regarding an accurate wording of marginal conditions, but I believe that's a question not to the applicant, but rather to the school that he represents, because he follows the school tradition of setting such conditions. And a few questions that I wanted to solicit your answers to. It's about the physical reality of M that equals 16, one of the examples. So you have my questions. And also, how we explain the provision of independence of superficial energy. Mikhail, I believe, takes this gradient into account in his work. So it's interesting to study whether you so it's interesting to learn whether you studied the effect of sign of longitudinal stress in problems considered in chapters 2.4, in chapter 2 and 4. And just a wish for the future, judging by microphotos of the curved planes, the relief can be described as cycloids. And some authors, like Shuvalov, they used this perturbed surface, and it would be nice to compare whether the critical values will change in this case, and how much. But still, these remarks do not compromise the high value of the work, and I believe that the work overall corresponds to the requirements to the thesis. Thank you so much for the questions. I will not answer those that were already discussed. As for the value of a superficial roughness of 60 newtons per meter, in works on molecular dynamics that define these parameters, there are not a lot of materials that were studied, and overall surface rigidity does not exceed 30, but we should take into account that these values can differ depending on crystallographic orientation, depending on other factors, whether we had pre-stress or not. And in fact, we decided to consider certain ranges as a condition, and we took this as a conditional upper limit, 60 newtons per meter. And I can't give you the material that corresponds to these characteristics, but this does not include the existence of such a material. And the question was, there was yet another question about whether we took into account the influence of the sign in the second, third, and fourth chapter. In these chapters, we concentrated on superficial elasticity, and the sign impact was not studied there. And as for your recommendations, yes, further on we plan to consider other perturbations forms, and we have devised a specific approach to that. And in further studies, I'll do that. Okay, thank you. Now we shift to the speech of... Oh, I forgot. So the speeches of the guests who are not members of the board, if there are any comments. Yes, please. Yes, Anatoly, please introduce yourself. So you don't see me, yes? Yes. Yes, and we'll include it into the list. Okay. Bachkarov Anatoly Olegovich, Associate Professor of the Department of High Mathematics of St. Petersburg State University. The question was discussed, I believe you raised it, about taking into account the gradient summons in Girton-Murdoch model. Well, initially, when the applicant described the general idea of this model, mentioned that the model provides for two phases, two different elastic phases, which is not fully correct, because beyond this elastic phase of coating, beyond this phase, we have yet another phase, the tension of liquid, that is a component of the superficial elasticity. And bearing it in mind, in a non-standard manner, in pure elasticity models, we don't know what to do with it. And in many models, it is ignored. And Gleb also did not consider it. And as for this question, quite frequently I was interested in it, whether we need to take it into account or not, because there is something that interferes, and the general elasticity theory methods collapse here, and what should be done about it. But still, literature analysis shows that the different researchers are trying to take it into account. And as for tangential direction, this model is justified because the impact is insignificant. But as soon as we have a curve, we have normal component, and this superficial stress starts to work. Therefore, everything that was not dealing with the fact that it was not taken into account is justified in this case, I believe. But the higher the fluctuations, the higher the amplitude, the normal component becomes visible, and we need to consider the impact. So that's the comment that I wanted to make regarding the consideration of this important element of surface. Thank you, Anatoly. Thank you. Anyone else? Do I have any questions submitted online? None? Okay. Then we give the floor to the thesis supervisor. Sergey, please tell us about the applicant and his work. Yes, thank you. The work was rather holistic to my mind, due to the fact that Gleb started working on the topic during his bachelor studies, and during that time he moved forward a lot, and as we could see, the model became more complicated in time, and he added up summands that allowed to take into account the surface elasticity, and this allowed to get new results, and they are not described and published by other authors, maybe in some theoretical issues. But if we talk about numerical analysis, then superficial stiffness and the impact of superficial stiffness on the formation of relief was not studied. And these results are new. And Gleb is really quite an active researcher. He participated in conferences, and I believe his publications were mentioned. He published 8 works, and part of them was published in first quartile journals, and he attended a lot of conferences, Russian, international ones as well, and this work was supported by the Russian Foundation for Basic Research, and Gleb successfully kept with all the reporting procedures, with all this formal part of the issue. And once again, I would like to repeat that the thesis is a finished work, rather holistic, and it deserves the academic degree of the Candidate of Sciences. Thank you, Sergei. Does anyone wish to comment as well? No one? Okay. Here we stop the discussion. And before we draw the conclusions, I would like to ask the members of the board if there is a need to do the members of the board or the applicant have any questions about the procedure of the session, maybe associated with remote access regime. No questions? Okay. Then let's shift to the next item in our agenda, the vote. Distinguished colleagues, before the vote, we have an opportunity to announce a short break to discuss the results, and this discussion will not be broadcast. How do you think? Do we need such a break or not? So, Alexander, do you want to have a closed discussion? Yes. Okay, then we announce a technical break number 1. Oh no, closed session. Okay, I announced the closed discussion, and I kindly ask to turn off the microphones and sound. And everyone else, please leave the room. So I therefore close our 5-minute discussion. And now it's 21 minutes past 3. So we continue our session. Dear colleagues, the broadcast is on. And let us check whether we all hear each other. Professor Altenbach, do you hear me? Yes. Yes, I do. So I therefore raise a question on the award of the academic degree of the candidate of sciences in physics and mathematics to Gleb Shuvalov in specialization 118, mechanics of deformed solid body. And we're going to have open balloting. And I would like to emphasize that voting for every member of the board agrees that Article 11 of the order is not violated by the candidate, and I would like to quote it. So, Article 11, in the thesis, the applicant for the academic degree is obliged to cite the author and or the source of the material or individual results that were borrowed. Using the results obtained by the applicant personally and or in co-authorship, the applicant for the degree is obliged to note this circumstance in the thesis. And let me remind you that the decision of the Dissertation Board on conferring or non-conferring the academic degree, so the decision of the Dissertation Board on conferring the academic degree is positive, provided more than half, but no less than 3 members of the board voted in favor. And that's in conformity with section with Article 17 on the order on the procedure of granting academic degrees at St. Petersburg State University. That's it. So let's vote. Svetlana Bauer, what's your opinion? I vote for the award of the academic degree to Gleb. Then Professor Volkov, what's your opinion? I believe that Gleb deserves the award of the academic degree. Now, Elena Vilchevskaya. I also vote for the award of the academic degree. Thank you. Professor Altenbach, what's your opinion? Yes, he deserves, no doubt about that. And I, chair of the board, Yulia Pronina, also believe that Gleb Shuvalov deserves the academic degree of candidate of sciences in physics and mathematics. Therefore, distinguished guests and colleagues, I would like to announce that out of the 5 members of the board, 5 voted in favor, no one voted against, and no one abstained from the vote. Therefore, we decide to award the academic degree of candidate of sciences in physics and mathematics to Gleb Shuvalov in specialization 118, solid mechanics. And the decision is unanimous, and I give the floor to Gleb Shuvalov for the finalizing remarks. Thank you so much for the appraisal of my work. First of all, I would like to beg your pardon for all those misprints, and I understand that you paid a lot of attention to studying my work. And I would like to thank, first of all, my parents for their support, for their understanding, and I would like to thank my department and all the teachers of applied mathematics and control processes. To our entire faculty, I would like to thank my friends and my relatives for supporting me, and I would like to thank St. Petersburg State University for all the opportunities, and I would like to thank all the board members for the valuable remarks, because you outlined the vector for further development to me, and thank you everyone who supported this event, to the technical team, to translate, to the interpreter, and I would like to thank my thesis supervisor, Sergei Kostyrka. Thank you so much for your advice, for corrections, for support, for patience. because certainly this work will not be possible without you, and I'm really grateful for that. So we congratulate Gleb Shuvalov with the award of the academic degree. And I therefore close our session. I'd like to thank everyone, and please turn off the...
Всем